Good, just in case. I'm going to talk about section 6.6 today. This is still in the chapter on inverse function. So we have studied exponential function and the inverse to the exponential function, that's logarithm function, and we memorize those formulas. And so there are other elementary functions we should know, like sine x, cosine x, trigonometric function. Okay, so we're going to have a quick review on the sine function, cosine function, and tangent function. Then I'm trying to understand the inverse and their derivatives. That's all we need. Okay. Most of the time we pay attention to sine x, cotangent x, and then inverse. Okay. So let's recall the sine x. Okay, sine x. The whole graph, when we say sine x, without measuring the interval, that will be the function define the whole line. Okay, so y equals sine x, and then without the restriction x, and the domain will be the whole line. So in that case, this is a graph. This graph looks like everybody knows that, right? It's periodic function, and that's a periodic function. And here it's going to be pi. That's 2 pi. Okay. But how do you define the inverse? If this is a sine x, it's not a inverse. It's not an increasing function. It's not a decreasing function. So you are not able to define the inverse. So you have to cut one piece. Okay. We are going to consider the sine x, the following piece only, which is going to be f of x equal to sine x, but the x is between negative pi and positive pi, and then we can include those two endpoints. So that small piece, okay, let's draw the curve here. It's going to be like this piece, this is the red curve, okay? So that piece is going to be increasing function, right? Okay, only that piece. It's pi over 2. Here's negative pi over 2. So for this function, it has the inverse. Basically, you can solve for, in the abstract way, it's just f of x, right? Then you solve for x in terms of y, you get the inverse function. So in the same way, if we have sine x, sine, S-I-N, is just the name of the function, specific name for that function. In general, we just use the f. We use 3 letters. Well, of course, we have to use more letters to denote a name, right? Just like your last name, maybe consists of 5 letters. The same. You cannot use A and B and C, right? Otherwise, be confused. Right? So when you try to solve that, then x, then this sign, we put a negative. Okay, this is not negative power. It just means the inverse of sine of x. Okay, so this is the inverse exists. Okay. And the graph of this equation, those 2 equations are equivalent. It's the same equation, just in different form. So that corresponds to the same graph. But if you want to interchange the variable, then the graph will be different. Okay. So how can I draw the graph? So let's try this. Okay. This is the middle line. Okay. I believe that this is the graph would be looks like that. This is already in the graph. Okay, so this is a sine function. Okay, y equals sine x. So the inverse will be the graph symmetric to that one. And let me use a different color, a little bit color. Okay, so this will be y equals of the inverse function. They are symmetric about the line after you interchange the 2 variables x and y. Then you get 2 different functions, 2 different equations. Essentially, they're different. Then their graphs are symmetric to each other. Okay. Now, So what is the domain for the new function? For the x value, I think it's clear that x is between this time. We probably don't want to include the end point, okay? X is between negative and positive 1, okay? For this function, y is between negative pi over 2 and the positive pi over 2. But for the original function, here x is between negative pi over 2 and the positive pi over 2. The reason we don't want to include the end point, we don't want it, okay? Otherwise, we have to differentiability, you know, involve too much technical stuff. So here, the y is between negative and positive. So the domain of the original function becomes a range of the new inverse function. So those two are correspondence. Those two are correspond. Okay. So that's all about the inverse. And based on the general formula, right? The relationship, if you want to put the sine x and the sine inverse, right? And then you should get x. X is between negative pi over 2 and the positive pi over 2. And the same, similarly, if we put sine outside, sine inverse inside, you also get x. You can put the y there, you know. Then x is between negative and positive 1. Okay? Those are the two identities. It's very important identities. We use that to find, we use that actually to find the derivative of the inverse function. So our next problem is to find the formula for the inverse function. Okay? Find the formula for the inverse function. Remember, the inverse function, right? And that's the definition. The formula is going to be 1 over sine prime, right? I hope we still remember this. You know what? Because compared with the most general one, right? Here, f just replaced by s sine, sin. So this is the general formula implies the special formula. Right. So in order to find the inverse function, the derivative inverse just need to find and that. But we know sine prime is going to be cosine prime, right? So it's going to be cosine prime. Okay, now, are we able to simplify this further? This is a very general, right? Sine becomes cosine. And let's do it. Okay, it's possible. All right, we're going to simplify, okay? We let theta to be the inverse of x. We want to find the cosine theta, right? Then you can simplify the denominator. Find this, express it in terms of x. How about this? But this really means sine theta equals x. But we also know that theta is between pi over 2 and positive, between negative pi over 2 and positive pi. Right? This theta, yeah, it's equivalent to the following two statements. Right? So we want to find the cosine theta, but cosine theta and sine theta, essentially, they're not brand new independent functions. They're related. Sine and cosine. It's just for the convenience, we introduce new notation and for so-called cosine theta. Okay, but sine theta and cosine theta, they are really not, they're connected like a twin brothers. Okay, they're always associated to each other. They're connected by the Pythagorean theory. We have always this identity. So if you know the value of sine theta, you know the value of cosine theta. Even you don't need to know the exact value of theta. Okay? And the only worry about is the sign, whether it's positive or negative, because it's squared. Okay? So, okay, you want to find the cosine theta. So cosine square theta equals 1 minus sine square theta. And what is sine theta? Sine theta is just x. So great. It's 1 minus x squared. Okay? Then cosine theta is going to be plus minus 1 minus this. All right, so now we have to determine the value of cosine theta. Can we determine the sign? Is it positive or is it negative, or sometimes positive, sometimes negative? Right? Sometimes positive, sometimes negative. So let's see. We go back to look at the theta, where it's from. It's from the inverse of sine x. So that means from the definition of the inverse function, theta is between negative pi over 2 and positive pi over 2. So for theta is in the first quadrant and fourth quadrant, first quadrant and fourth. For such theta, cosine theta is positive. Okay, so cosine theta must be positive, and so you get this since cosine theta is positive for theta between in the interval negative pi over 2 and positive pi over 2. This is a review of a trigonometric geometry. Okay, so now you put it back. This is going to go back to here. Okay, theta is x, the inverse of sine x. So now you get, okay, this is a cosine theta. It's going to be 1 minus square x. Okay, so we get very important formula. The inverse function of sine, the derivative can be expressed without using trigonometric functions. Because trigonometric function is more abstract than radicals, right? Than polynomials. So we want to express, if possible, express them using more elementary functions. Okay, so sine, cosine, those are the functions induced by human being after we understood polynomials or radical functions. Okay, so maybe in engineering, when you are dealing with some equations, and if we prove that the solution exists, but it cannot really describe the solution using well-known elementary functions, then what? Then you probably can name it, right? You can call it any name you like, and then you have to study those functions, describe the behavior of those functions near infinity or any singular point, and then sometimes you're lucky the inverse exists, but the derivative inverse can be still expressed in terms of more elementary functions, like in this case. Okay, we have a elementary function at different levels. The first level, sine, polynomials, x squared plus x, blah blah. The next level is like a square root of x, the square root of x squared plus 1, something like that. Then above that will be sine, cosine, and more abstract, right? And so you see that the inverse function, the derivative still can be expressed by more elementary functions than the original function. Okay, so this is a formula, and similarly, you can find the derivative of the inverse cosine x. But anyway, so let's say if you have a formula like that, then immediately, if you see an integral, then this is going to be the x sine x plus c, right? So those two are due to each other, okay? You have a derivative and have an integral. You have an integral, then you have a derivative, okay? All right, how about sine, cosine? How about cosine? Okay, for the cosine, you can also find the inverse. Let me quickly talk about the inverse of cosine. So why cosine x? Well, the graph of the cosine x is a very it's still not an increasing function. It goes like that. Okay, it's shifted by pi over 2. So here, pi over 2. I think this will be 3 pi over 2, and this will be 2 pi. Okay? It's periodic function. So which piece you can cut to define the inverse? And we decide, okay, doesn't matter which piece you're going to choose, as long as it's either always decreasing or always increasing. So we choose that piece. Right? We choose this piece. Yeah. So this piece will be used to define the inverse function. So we'll consider y equals cosine x, but the x is between 0 and pi. Okay. Right. Then you can talk about the inverse. You can solve for x in terms of y, right? Then you can also exchange the variable. Okay, those two, those two, the last two equations are not equivalent. Those two equations are equivalent. Okay, they're just the relationship between x and y in different forms. But the third one is brand new equation. You change it. It comes from the second one, but you already interchange two variables. So in that case, the graph for cosine, the inverse of cosine x is different. Right? So you get, right, that piece, that's the original, y equals cosine x. So how can I draw the one symmetric to that? It's a little bit challenging. Okay? So you have to copy, it's a little bit hard, yeah. Let me try. All right, so that's it. Why be like this? And this is the pi over 2. Pi over 2 is larger than 1. This is value 1, so this should be 1. Pi over 2 is larger than 1. Pi over 2, pi is 3.14, right? Divided by 2, it'll be 1 point something. Okay, so this is so 1 is on the left-hand side of pi over 2. Okay, so this is a graph y equals arcsine. So if you don't, so look at this. So what is the domain for the inverse function? The domain for the inverse function, x is still between -1 and +1, right? Right? And the y value is between 0 and pi. And for the cosine function, x is between 0 and pi, and the y value is between -1 and pi. Okay? So the domain of the original function between 0 and pi, this becomes the range of the inverse function. Yeah. But anyway, using the same idea, I want to give you the derivative of cosine, which is nothing but change the sign for that. So the derivative of a cosine is going to be this. All right. Now what you can get, this is a formula, right? So you have so the inverse, the integral of this function, right? Because this is always the same as negative arc cosine x, right? So you can always get this, right? But you can also get a negative cosine x plus constant c. Then the question, okay, this is c is a different c, okay, that's called c1, let's do c2. Okay. Then you get something interesting, which is we call it in mathematics we call it corollary. What they said that arc sine x plus arc cosine x is always equal to a constant. Okay, now that domain is different. Okay, so let's see, what is that domain? Domain for the x, yeah, for x is still x between 1 and +0. Okay, so same domain. Okay, that's okay. So what is that constant? Because why that it's constant? Because you move cosine x, arc cosine x to the left. You add them together, right? So question is, what is that constant? Think about. What is that constant? Huh? You can choose a special value for cosine for x. You just look at, okay. So arc sine 0 is going to be 0, but arc cosine 0 is going to be, if you don't know, look at the picture. Okay, arc cosine 0, this is a pi over 2, right? So when x equals 0, arc cosine 0 is going to be pi over 2. So arc, yeah, cosine 0 is pi over 2. So that constant is just pi over 2. Okay, so we discover that this is a pi over 2, okay? We discover that those two functions, arc sine, arc cosine, is really, they're really not completely different functions. They're just different by constant, right? Yeah, so they're not brand. If you know arc cosine x, you know arc sine x, yeah, Sometimes we don't say inverse of cosine, just arc sine, arc cosine. That's different notation, okay? So this is a notation in mathematics, okay? So, yeah, arc cosine, maybe just make it easier to pronounce. All right, so those are the functions and the inverse and the derivative. Right? Okay, so let's do some exercise from the book. Now, what kind of problems usually would be on the test? Well, sometimes you do have to, yeah, like that, like this. If y equals arc sine, for example, square x, okay? Find the derivative y with respect to x. Okay. This is a composite of two functions, okay? It's composite of two functions, and yeah, how to find the derivative of this function? Okay. Find yeah. Right, so this is inverse, right? The inverse function. So derivative y with respect to x, that just differentiate the arc sine, then also have to differentiate the inside function. This is a channel. That's a channel. Okay, so that it's not product. Here's just the derivative of the inverse function. The derivative of the inverse function will be 1 over square root of 1 minus whatever here is should be square, right? So square x squared, and the derivative of the square x is going to be 1 over 2 times square x. So you have to simplify it. You will get 1 minus x and the 2 square x. Okay, so this will be the answer. Okay, this will be the answer. Hmm? Can't you simplify it more than that? Well, simplify a little bit. You can also combine them into one radicals. Yeah. That's about zero. And we look at another examples. Okay, this is from the book. We are given sine f of x is the inverse of 1 minus x squared. Okay. Ooh. This is a dy with dx. Okay. So we want to find, the first question is find the domain of f. The derivative of the function and the domain of the derivative. Okay. So there's three questions here. So first of all, you look at the arcsine function. Okay. If you don't remember the domain of the arcsine function, go back to the graph. Okay. How do we define it? So the graph, let's go back quickly, right? See, the input for sine is between negative pi and positive pi. The output is between negative and positive. So now you're talking about inverse. So the domain of the inverse should be the range of the original sine function. So that means the domain of the function will be x, 1 minus x squared between negative 1 and the positive, right? This is not an angle. It's not like between pi over 2 and positive pi over 2. So you have to solve this inequality. Yeah, you have to solve this inequality. Okay? So let's solve this inequality. So negative x squared is less than 0, greater than negative 2. Right? You move 1 to the both sides. You multiply negative sign, that's become, okay? It's become, you have to change the direction of the inequality. Okay? You have to change the direction of the inequality. Or you can write like this, x squared less than 2, greater than 0. When you multiply this inequality by negative 1, you have to reverse all the directions of the inequality. Okay? And then x squared is between 0 and 2. How can I solve for x? Okay, clearly x can be negative. Be careful. If x is positive, then x will be, if you just solve this inequality, right? Then this is equivalent to saying that absolute x is less than square root 2. This is equivalent to x between negative square root 2 and positive square root 2. Okay? But there is to say, it says x greater than 0. That means x cannot be 0. So for this one, I think the solution will be the interval from negative square root 2 to positive square root 2, but 0 should be excluded. Okay? So be careful about that. So this is equivalent to saying like that. Okay? So forget the 0 on the left-hand side. Then you do get the same inequality, but x should be excluded. Okay? So x is going to be, the answer will be x. The answer will be a little bit difficult to say here. Answer is greater than negative square root 2 less than 0, or x greater than 0 less than square root 2. Okay, so that is a domain. So let me write down the domain. Okay, so this is a domain. Okay, so now let's find the derivative. According to the definition, the formula for the derivative, okay, f prime x, this is a what? This is the inverse, right? So you get sine prime and, sine prime and sine inverse 1 minus x squared, right? So, no, sorry, we don't want to use the original one. The original one is too complicated. So we just apply the formula directly. It's going to be square root of 1 minus whatever is inside, that's square. Then you differentiate the 1 minus x squared. Okay. Now, Some common mistakes will be students will just put the square root of 1 minus x squared. But that's wrong. You have to move, you have to put the 1 minus x squared, okay? Yeah. So derivative of the inverse, this one will be, right? But you have to, here x is replaced by 1 minus x squared. So that's why you have to put 1 minus x squared, then squared, okay? So your function here is a function here, you see, this is a function, it's the inverse on the very top. Inverse sine and parenthesis 1 minus x squared. All right, so let's simplify a little bit. It's going to be negative 2x, that's numerator. Denominator, I think it's 1 minus 1 minus 2x plus x to the fourth power. So further simplification, we get 1 will be canceled out, 2x squared minus x to the fourth power. Now, can you simplify a little bit? It's possible. I can take x squared out, right? I can take x squared out. That'll be square x squared, 2 minus x squared, negative 2x. The question is, I don't know whether x is positive or negative. So the only way I can do is change to get rid of square root. Then, how can I simplify? How can I cancel x and absolute x? It's really depends on sign, right? When x is positive, I get negative 2 over if x is positive, right? And it's negative, absolute of x will be negative, so it's 2. Okay, so x cannot be 0, clearly. So in each side, on each side of the interval, yeah, there are 2 intervals here for the domain. In each interval, you get an expression for the derivative. Okay? So if you find, so the domain of the derivative, I think is still the same domain as the derivative, as the original function. Because look at 2 minus x squared, right? X cannot be 0. 2 minus x squared must be positive, then x must be square x, you know, x, absolute x must be less than 2. So as I think it's obvious, the domain of the derivative still the same, okay? Which is the original function, the domain of the original function. All right, so after these examples, let's go to the tangent function. So y equals tangent function. Okay, do you remember the graph of tangent function? There are many pieces, but they are periodic. Yes?
Does that happen very often?
Split it into 2 or 3?
Yeah.
No, not very often. Yeah, I just randomly pick a problem that I find out the domain, yeah, of the original function is not a one single interval. I'm trying to solve. Okay. But you have to prepare for that, this type of problems. You know? Okay? You don't know, you know, yeah, what we are going to give it. Okay. All right, so tangent x, y equals tangent. So we have to know the graph of tangent x. The graph of tangent x, you know, I usually just memorize the properties of sine, cosine. Otherwise, too much, you know, right? And in the future, we human beings will depend on devices more and more. Okay, so you don't need to memorize lots of things. Every time when you need some information, look at cell phone, blah, 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 and find it. It's so convenient. Okay, so everybody become very smart and knows lots of things quickly within a few seconds if you know how to use the solve formulas. All right, so this is a sine x, cosine x. But nowadays, even you save your time. I remember I went to one student's bedroom, and he just say a few words, turn on the lights. The lights is on. Right? You don't need to push the button somewhere. Okay, that's cool. Right? Save you time. You just walk into the apartment, and everything is ready for you. Maybe even rice cookies already. The food is ready. You don't need to crash. That's possible. Okay. Okay. Yeah. And so. Right, sine x over cosine x. So clearly, when x equals pi over 2 or negative pi over 2, it's not defined at all. So the graph, you see, those are the numbers have to be excluded, right? So we call that asymptotes. So the tangent x is just a graph of like that, and it goes to when x approaches pi over 2, the denominator approaches 0. And from positive side, numerator approaches, and think about how to get this graph. As x approaches pi over 2 from negative side, right? Then you will see that cosine x approaches 0 from positive side, but sine x approaches 1. Doesn't matter which side, it's always positive. So that's the reason the quotient, which is tangent x, approaches positive infinity. Okay, this implies tangent x approaches positive infinity. That's why how do you get the graph? All right, that's good enough. This graph is increasing. Okay, therefore the inverse exists. I just need to focus on tangent x over that interval. I don't want to. This is a periodic function. That piece is enough to define the inverse. Okay, when you define the inverse, what you should do, okay, this is a y cos tangent x. You draw the line, middle lines. You draw the middle line, okay? Yes. You draw the middle line, and then the inverse will be the graph of the inverse. You see? So let me complete all the arguments. So y equals tangent x. Then you solve for x in terms of y. Then you interchange the variable. Okay? And as you get interchange the variable, I'm going to change the color. I prefer the red color. Okay. So this is a y equals. Then you can see the range of the inverse function, the domain of the inverse function. I think the domain of the inverse function will be the whole line. And look at the domain of this, right? Of the original function. The range of the original function will be from negative infinity to positive infinity, right? All right, so it's positive infinity. And here it's the same. You don't need to worry about it. Then the inverse function, the domain will be the range of the original function. The range will be the domain of the original function. So yeah. So now it's clear. Okay. So we get the inverse. Now we have to find out. It's good exercise. You have to find the inverse, right? The derivative of the inverse. this is supposed to be the derivative of the tangent, then with the inverse. The question is, are we able to express that in terms of x, right? Okay, without using a trigonometric function. Now, what is the derivative of tangent? Secant squared. Okay, so derivative of tangent will be secant squared. Okay, so we have to express secant squared tangent x, arctangent x. So how do I do that? But then you let theta to be this, right? And you want to find out secant square theta, right? Right? Then you're done. This is a good exercise. So tangent theta is going to be arctangent x. Means two things. One, tangent theta equals x. Second, theta is not arbitrary. Theta is between pi over 2 and negative pi over 2 and the positive pi over 2, right? So we want to find the secant theta. If you know tangent theta, can you find secant theta? Yes. There's a very simple formula. How do you figure out the tangent theta, right? So 1 plus, let's see, 1 plus tangent square theta, right? Is going to be secant square theta. I hope you know this. This is yeah, we review, the formulas from trigonometric functions. All right, so we know already the tangent theta, so it's 1 plus x squared equals secant squared. Okay, great, simple, we find it. We even don't need to worry about the sign, whether it's positive or negative. So this gives to here, okay, we get, it's going to be 1 over x squared, okay? So next time if you see an integral like 1 over 1 plus x squared, then this will be arctangent x plus constant. All right. Okay, x is an arbitrary x. And similarly, you can find the cotangent x, cotangent x, just they are next to each other, right? Cotangent x is just going to be, if you remember this cosine x sine x, right? And this actually is going to be a 1 over tangent x, right? So they are inverse to each other. It's not like a sine cosine relations, cosine squared plus sine squared equals what? Actually, cotangent x times tangent x equals. It's not, okay? So, but we still can find cotangent x is defined. Cotangent x, I think it's defined from 0 to pi. Yeah, when x equals pi over, when x equals 0, the both sides not defined. So let's look at the cotangent. What's it? How the graph looks like? I think between 0 and the pi over 2, cotangent x is positive, but between pi over 2 and pi, cotangent x is negative. So it's decreasing function. So if you draw the graph, for cotangent x, it will be, you have to draw it in a different way. As this point goes to here, right? It's flipped over. It's difficult to draw it. Okay, so the domain Yeah, I think goes like this. Yes, good. So 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 x is between negative infinity, but the y variable for the inverse will be between 0 and the 1. Okay. So I'm not going to waste too much time on the cotangent because most of the time we're not going to use that. But the derivative is nothing just equal to negative sign of this. Okay. So we know yeah, this is how do we get the derivative for the cotangent x, inverse of cotangent x. All right. Let's see if any examples we can discuss. There are just too many. Yeah. All of a sudden we have to study several. As you see that the derivative of inverse, you see the derivative of the inverse function, right, is going to be positive this, right? So if you add them together, okay, this is going to be, first one is positive, the second one is negative. It's going to be 0. So that means that the inverse function of tangent and the inverse function of cotangent will also be a constant. But how do you figure out the constant? You just need to plug. I think what's the definition? Plug. We have to put the value for that, right? X is for anywhere, so plug 0 for x. So this is going to be okay. Arctangent 0 is going to be 0. Arccotangent 0 is going to be, it's here, the picture is here. So this is going to be pi over 2. So it's pi over 2. It's pi over 2. So that constant is pi over 2. So arctangent x, arccotangent x, they are essentially the same function. So that's the reason we just need to understand arctangent x and arcsine x. Okay, because they are, remember, they are not brand new functions, arccosine x. Okay, so that's the reason, yeah, put this way, arc cosine x is a pi over 2 minus arc sine x. Arc cotangent x is also pi over 2 minus arctangent x. So they're not the essential new functions. So we don't want to talk about. So in the future, in many problems, we only use arc sine x, arctangent x. We're not going to study other functions. All right, let's do some exercise. Okay. So let's evaluate the integral of, oh, okay. What is that? Integral of arcsine. Integral of arcsine. How can I do that? If you know the integration by parts, okay, it's called integration by part. Sometimes I'm confused. It's belong to math 165 or 166. But if you took 165 before, have you heard about integration by parts? Yes. Okay, so let's do it. So integration by parts, because otherwise you cannot evaluate integral, right? Remember this problem x e to the x dx, for example, for such problems, you have to use the integration by parts. Okay. Anyway, but if you don't, I have to double check, okay, because sometimes I cannot remember which one belongs to which set. Yeah. But anyway, so this is part, that's part, right? The idea is like that. If you have a u and a dv, so you have a uv minus interchange, okay? Exchange, okay? So here x is v, u is arcsine. So this is going to be x. Yeah, u is a arcsine, so you just change the variable, okay? And here's x minus interchange, okay? So v is x, and the derivative of arcsine, okay? The derivative of arcsine is, you see, when you differentiate arcsine, it's going to be the derivative of arcsine x with respect to x in dx, okay? Okay, so that is going to be square root of x squared and dx. Okay, so let's put this. Okay, I change the order of the above function. Minus x, and this is going to be 1 minus x squared and dx. Okay, that's not the end of the story. We have to evaluate the integral, the second integral. And this integral will be easy, just use substitution. Use substitution, you let u to be 1 minus x squared, and du equals negative 2x dx. Okay, so this will be square u, right? 1 minus x squared is become u. And x times dx will be negative 1/2 du. Okay, yeah, you solve for x times dx. So let's simplify a little bit. And this is a negative becomes positive. And this is 1/2. U is in the denominator, so it's going to be negative 1/2 du, right? So you find the entire, this is substitution. So you find the entire derivative of that function, and that's going to be 1 minus negative 1/2 times u to the 1 minus 1/2 plus constant. All right, so now you simplify this. 1/2 is gone. And just u to the 1/2 plus c. So what is u? It's a 1 minus x squared. Okay, it's done. So you should know how to use substitution to evaluate the integrals, but the integration by parts, I have to double check. I believe that this belongs to Math 160. 5, this is a very standard technique to evaluate the integrals. Few words about secant x and how to define the inverse of a secant. We're not going to have a cosecant x, right? So secant, so we essentially have 3 functions and 3 inverses: sine, tangent, secant. Secant x, if you don't remember secant x, this is the 1 over cosine x. So which piece we're going to use? That's the problem, okay? If you draw the graph of secant x, it is really yeah, it's harder to draw it. It's pi over 2, 3 pi over 2. Yeah, this will be 2 pi. So the graph looks like that. And the graph looks like that. And then the graph looks like Okay, this is a graphs. Okay, you can draw that using cosine x, the value of cosine, when it's positive, when it's negative, and when x approaches power 2 and 3 power 2, one of our cosine x approaches infinity or negative infinity. That's the reason. The question is, how do you define the inverse? Okay, how do you define the inverse? So we use those two pieces. One is this piece. Okay, another piece will be, that's pretty strange why we have to use this two pieces. This is two pieces broken, but clearly it's one-to-one function. Okay, so you can find the, so the inverse, we only consider x between 0 and pi over 2, and x between pi and 3 pi over 2. Okay, this is the pi. Okay, so the domain of the secant function, which we use to define the inverse, is broken. Two pieces. Okay, so now the inverse will be y equals secant x. In that case, the domain, here you see, here is the domain of the range of y will be greater than or equal to 1, okay? So that's for the original function. And for the new function, and clearly x is greater than or equal to 1, right? The y is going to be between 0 and pi over 2, and the y is between pi over 2 and 3 pi over 2. Okay? And if you find the inverse, we do find that. We find the inverse. I'm sorry, I don't need to include the endpoints, otherwise we still have problems. So let's erase this equalities, okay? So make it easier to talk about derivatives. So when we find the derivative, this is a formula. The derivative of secant x is also can be expressed in terms of the element function. Okay, so clearly the domain of this will be greater than 1. Okay, and you can see that as absolute x should be greater than 1. Otherwise, as the denominator is not going to be defined. Okay, so this one we don't have much to say, but all you needed to know is this formula. The derivative of the inverse of secant x is going to be 1 over x times square of x squared minus 1. And it's defined, secant x is defined for x greater than 1, absolute of x greater than 1. Okay.